Welcome, everyone, to today's lecture, which is, again, on the same topic of visual imitation, learning by observation. Once we're done, we're probably going to enter into the, a little bit to the new topic of self-supervised visual learning and its use in visual reinforcement learning. We had concluded Monday's lecture with this work that showed how can you learn agents that do pretty fancy acrobatics in physics-aware simulation environments while imitating YouTube videos. Each policy that you see here on the agent uses a single video from the demonstration. I don't know if you remember what we said. We used computer vision technology to convert the 2D video into a trajectory of three-dimensional mesh for the human body. Okay, if you remember, we used the simple model, which was a parametric mesh model for the human body that maps 13 parameters of shape and pose into the locations of 30,000 node vertices of the mesh. So the computer vision technology or learning technology that we presented, essentially its job is to estimate those 13 parameters for every video frame. We said that the way to do that is using simulation data, where you take random backgrounds, you render the simple model, you texture it, and you train a neural network to take the resulting frame and infer those 13 parameters. So that was very simple that we said. On top of that, there is a self-supervised loss terms, self-supervised objectives that you optimize at test time for every video. And those self-supervised objectives had to do with 3D to 2D projection, if you remember. So our goal here was to go from 2D to 3D. So how do you do that? There is the reactive part that takes the image and spits out those 13 parameters that essentially render the 3D mesh. And there is the self-supervised part where you render back the 3D mesh to 2D and see how well your inferred 3D model matches the 2D observations, okay? And the 2D observations that we matched against was key points, okay, detected key points, 2D key points, optical flow, the motion. So we wanted the 3D motion when projected to match the estimated 2D motion, as well as segmentation mask, if you remember, okay? And why I'm repeating that? Because if you want to go beyond imitating the human body to imitating, for example, general interactions of humans from video. So you see here this guy, he's using the mic. And what you want to do is you have a robot that wants to use the mic in similar ways. Okay. Now, the problem is much, much harder because we went from a closed world, the world of human body, which we know super well. We spent a lot of money trying to make that simple model, okay, from, scanning human bodies on our scanner and aligning them and so on, and annotating insane amount of images of those 2D joints to an open world of bunch of different object categories. And now here is the catch here in this paper. To do that, we're going to do something very similar. We're going to take the video, whatever you say on the top, and we're going to infer the 3D trajectory of the human hand as well as the object, okay, in 3D. Everything is in 3D. Again, this is computer vision technology. Okay, are you guys understanding what's going on? Okay, now the result of those key points of the human hand, but mostly of the object, because our robot hand will be very different than this human hand. The only way we infer the human hand is to be able to jointly reconstruct the hand and that 3D object and render it and make sure we take care of occlusions so that when there's a human hand, we know it's in front and we don't render the, the object, right? So we do ray casting when we do 3D to 2D for adding our reprojectional losses. So what are we going to try to imitate is essentially those trajectories of those objects from those videos, each passive video in the simulation environment. So we'll do exactly what we did before, but instead of imitating key points, we imitate object trajectories. So each time you move the mic in a way that it doesn't follow the trajectory that you infer from the video, you get penalized. Is that clear? And again, the reward is very dense in time. Okay. All right. Just to put this in perspective, this is all about visual imitation that has to do with matching visual features from your execution environment to the teacher's environment. All right? You generate something, you pick up this, you pick up the mic, you make a soup, okay? Or you fry an egg, and you want to make sure the visual features should look like the visual features of the teacher when he was, frying an egg. Does this make sense? And the question is, how do you represent the visual state? And we saw last lecture 2 ways. One was you take a whole frame and you featurize it, you make one vector and you match those vectors. This was in the playing difficult exploration games by watching YouTube. And then here we see something on the other, completely other, let's say, side of the spectrum, where instead of taking a frame and, making a generic unstructured 1D vector, they really try to segment every object, track every object, and imitate very, very accurately the pose of that particular object. What does this mean? This means that all these other things, the features of this guy here, all around, they go away. You only focus on the object you care about, you infer its poses over time, and then you try to imitate, okay? So the more accurate your computer vision technology is, the more fine-grained, the better you can imitate. Is that clear? Okay, and by the way, this is very recent papers, like this month came out, all right? But it is super related to what we saw before. So here is what they do. They do this inference on tons and tons of videos. Now, I want to ask you something. Before, we said that even there was a startup that gave to the community that simple model, okay, of the human body. Here that we have a gazillion set of objects, who's going to give us those models? Okay, who's going to infer from, who's going to do the job of taking the video frame and spitting out the mesh of the object? Is that clear? Because you need that. You need that. On top of that, you need tracking, a lot of things you need. But that's a part that we said that Michael Black actually made the startup in Germany precisely about that simple model, okay, that would have this low parametric, 13 parameters that control the shape and the pose. And then our job was just to predict those parameters. So now the question is how we're going to infer the mesh of the object in the first place here in this general case. Now the catch is the following. They assume that in each video, they know the 3D object mesh. Okay. Now, still the job is not that easy because you need to infer its rotation and translation over time, but it's for sure much easier than if you don't have a clue what's the shape of the object. Okay. Is that clear? Now, this is an unrealistic assumption, but it's not too terrible. I mean, you can imagine taking that approach and adding an extra step where you see the frame, you have a library of 3D meshes, why not? And you have learned, a model that, has the projections of each 3D model and tries to match what you see to which object actually this corresponds to. And we know that object classifiers actually kind of work. So you can run some object classifier. I mean, clearly, if you hold the object like that, the classifiers, there's no clue that is going to figure out where the object is, but there's going to be a frame of the video where the object is more visible. That's all you care to know. I mean, that's the beautiful thing about videos, that some frames are hard, but some frames are easy. Now, once you figure out what object it is, clearly you have a filtering of, okay, what could the 3D mesh be? It's a cell phone. Okay, it's going to look like a cell phone. Now, you only need to worry about resizing it and so on. And by the way, these people do infer size information, I think, during their self-supervised optimization. Now, I'm not going to go into the details of the losses, but I think it's good to read because you'll appreciate that if you really want to learn from videos and, really imitate the way humans do, you really need to go deep into the computer vision technology, feature matching, tracking, and so on. Okay, so that's why we added this paper. All right, this guy did the very simple. So what do? Do we infer now the poses, and then we go here and we do reinforcement learning. And as you see, the first iterations are not that great. But the beautiful thing here is we have dense in time reward. For every time step, we have how this object moves. Now, as soon as this guy makes contact with the object, is able to grasp it, then the rest is very easy, as you saw. You see, because the hard thing is to go and grasp the object. Now, they have added some extra rewards because they know that it's object interaction. And if you start your gripper there, they put a reward of, I'll reward you if you go close to the object. Okay. And let alone, I don't think it's that terrible to also have a specific grasping module that tells you how to grasp, etc. So I'm pretty sure you can do better reinforcement learning with this. But I would say it's pretty reasonable. They figured out how to pick up this in 2,000 iterations. Okay. All right. All right. So by the way, they don't have contact points here. They don't model where the fingers made contact with the object. I think that's also pretty useful. So if you add that, then you're in much better shape because you're like, okay, make sure you go there. Okay. So you add some more dense reward also for the chunk before you make contact with the object. So you can supervise densely all the way from the beginning, all the way to going, pick up the object, lifting up and so on. Okay. Is that clear? Which this is not what happens here. Okay. All right. Now here's another work. I mean, we're going to visit a lot of different papers today. You just need to I mean, you don't have a lot of required readings, actually, it's only 4, but we're going to visit multiple papers just to have the ideas. So what these people do, this is a famous paper. It's called Object Nets. It was a best paper award in Coral, maybe three years ago. Okay. And they have the extremely simple idea. This actually links to the topic of our next lecture of having an object, seeing that 3D object from 2 different viewpoints. Okay. And asking the projections of the same 3D physical point to have similar features. So they do this feature learning, and here they do PCA, and you see that different parts of this fancy animal have different colors, so you can identify them. You see, you invest a lot on these visual representations. And then what do you do once you are able to have those object descriptors? Then somebody can go and pick up the shoe for a particular location, all right? And you know where he picked it up, and you go and pick it up in the same way. Do you see? So I pick up a shoe, you see where I pick up. If you have good object descriptors, you can find the description of that location in another shoe and pick up the other shoe in the same way. It's all about the descriptors for a corresponding part of the objects to match. Okay? Okay, is that clear, guys? The same way that before we had the object key points, the human, like the elbow, then you want to figure out where the elbow is in all the images. Now you want to figure out where is the head of this caterpillar in all possible images. So if the human grabs the head of the caterpillar, you're like, yeah, here is the head. I'm also going to grasp it the same way. That's all. And how do they do this object descriptor learning? Well, this is all about self-supervision. Actually, is the topic of our next lecture. So you can also just wait, and we're going to visit such a thing. You see? So this is very, very beautiful. And these descriptors, by the way, these descriptors that you saw that they were following the motion of the caterpillar, they have nothing to do with reinforcement learning. They were only trained with self-supervised learning by looking at this caterpillar from different viewpoints and saying, yeah, put this feature close, put this feature far, a type of contrastive learning that we're going to see later. Okay? So without interacting at all, you just watch around, learn visual representations, and then zero shot, you can, imitate the human, etc. Okay. Now, this doesn't work all the time. For example, if you want to go up the stairs, you cannot just watch a human and you're going to learn to climb. Of course, you can figure out where to place your feet, but still you need to train yourself to hit these waypoints. And these are related to our earlier papers, right? The acrobatics. I gave you the waypoints you need to hit while doing the loop, but you really need to practice with PPO in your simulation to be able to hit them without the gravity really crumbling you, etc. All right. The same way that we actually can see the gymnast doing the flip and we really can parse her body. But for us to do the flip, it takes time. Okay. It is difficult. So that's exactly what our agent is doing. Okay. Now, other things, as you see me grabbing the chair, you're going to go and grab it. It's a very simple task. You don't need to practice that much. Okay. And this is precisely what these people are doing. Okay. So we actually presented a very related paper. Now, the last, do you have any questions, by the way? All right. So continuing on the theme of how do we learn by watching, okay, as opposed by interacting, and how do we have, by watching, being able to learn a policy with much, much fewer interactions with the world? A paper that we're going to visit now is called No Reinforcement Learning, No Simulation, Self-Supervised Learning for Actions. So we're going to use passive videos all the way for learning policies to navigate around in houses. Okay. Now I want to make sure before we were picking up the caterpillar, again, we were using visual representation learning for action. Okay. You were able to map your scene, figure out exactly which part of the object is in, as the object changes poses and how you move your head. And the actions were very simple in that case. We're just grasping a particular location and you were able to imitate it. And indeed, that's exactly the point I'm trying to make. When the actions are so easy, like navigate to a particular location or like grasping a particular location, you don't really need to self-try. It's not like you're going to learn to do a flip or you're going to go up in very complicated stairs or you need to learn to hop or learn ballet and so on. It's not that difficult. You just need to hit waypoints, much like in driving, right? The difficult job in driving is to predict the waypoint in the right, that you need to hit in the right time. Now, going to that waypoint, you're going to use a non-learning, low-level controller for the car. Does this make sense? That's it. So just to understand that there is maybe a continuum of difficulty for actions. In some, you can learn tons of things simply by watching where to pick up, where to place, and so on. And in some other tasks are difficult, and you may require a little bit of practice as well. But always learning the visual representations will guide your reinforcement learning to have much, much less interactions because it's going to give you dense in time rewards. This is the general theme. Is that clear? Okay. Now let's visit now our last paper to be able to move to our next topic as well. So this paper is upset to the previous papers that learn to do navigation with reinforcement learning. And now I want to tell you that there is a gazillion, there is a lot of emphasis from companies right now, Facebook, NVIDIA, and others, on building simulation environments for home robots, because they think that home robotics is a very big next thing. The same way we thought that self-driving cars also a very big next thing, and we built tons of simulators for self-driving cars. And in fact, every self-driving startup has a simulator, in-house simulator. So the same way now we want to do the same thing for house robotics, house robots. And I think the simulators look pretty incredible, to be honest. Okay. They look pretty incredible. Now, what happens with the availability of those simulators? Happens that a lot of researchers will say, okay, great, I have the simulation environment. The faster it runs, the more GPUs I have. The most obvious thing to do is I'm going to learn any task by just interacting in the environment, okay, using reinforcement learning. Another alternative thing that those researchers do is instead of just using reinforcement learning, they say, I'm going to collect some demonstrations on my simulation environment of things, of tasks, and then I'm going to imitate. So exactly what we'll be doing in our course. Sometimes we use imitation, sometimes we use RL, sometimes we use both, and so on. So the same thing here. Okay, so the task here that you need to worry about is semantic navigation. What is semantic navigation? I give you an object category, and I tell you, go to the chair, go to the toilet, go to the kitchen counter. Okay, there are not that many object categories that are being used here, but this is the idea of semantic navigation. I don't give you a location on the floor, go to 30,50. I give you a category. So what you need to do is you need to have your eyes open to be able to detect that object. And till you don't detect that object, you need to explore to try to find it. And guess what? When you tell you go to the soap, if you're searching the soap in the living room, means you don't have semantic priors. So that task also can, let's say, measure, how much common sense has your agent about where objects are. And also the common sense is not just about where objects are, but it's like when you're looking at this a picture, which way you think the restroom is going to be, okay? You're like, oh, maybe restrooms are usually to the left of the kitchens. I know that. So I'm going to try first to find it that direction. So they test these tasks, also your ability for general visual common sense of arrangements of rooms and objects in a home. Okay. So the way this task has been approached, not by everybody, but by many papers, is that I give you a goal image. So the goal, by the way, can be communicated either with an object category or with a picture. Okay. And then your job is to train an agent, a goal condition policy that conditions on the image and tries to predict which actions to do to get to that image the fastest possible. Is that clear? Is that clear? Okay. And it has we have seen a lot of progress in this problem, where the typical policy, does anybody want to tell us a typical policy architecture for this problem, what you would do? Or, I mean, clearly our policy needs to take as input images, right? Do you agree? Because it's a visual condition task. It also needs to take into account the goal image. So it needs to be goal conditioned, because I can guide your policy to go in different goal locations. Okay, but beyond that, how things are going to look like? Any baseline suggestion would be great. Just to have something concrete in our heads as a policy architecture. For this problem, yeah, what do you think? And by the way they train is standard PPO and so on and so forth. Okay, take your time. Yes.
You could regress directly from like the goal image and the sequence of previous images of where you're at to like motor speed and turning direction.
Yeah, sure. That's great. So your colleague says that you're going to take a history of previous images you've seen. So you need to have an architecture that can consume such history, like a transformer or STM or something like this, correct? And your goal image, and you want to predict what? The action parameters for the immediate actions, correct? Excellent. Yes, that's one way to do it. That's one very simple baseline. In fact, many papers use this baseline. Now, let me tell you what is the trick here. Unfortunately, when you train RL, you need a lot of simulations. And the problem is, if you have this backbone that processes images each time, then it becomes very slow. The RL that we've seen in previous, let's say, tasks, either uses XYZ of objects or uses much downsampled frames or not a lot of history, like 4 frames and that's it. So then the consumption is like things go much faster. So if you really want to build a reinforcement learning of such very rich visually policy, you really need to be using tons and tons of GPUs to be collecting experience and training in parallel and so on. Do you see the problem? Okay, but you can do that. That's fine. And then you can train an agent. And as you see here, there has been progress. The more steps you are able to take and the more GPU time you're able to use, and so on and so forth. So you consume resources and you train navigation policies. All right, is that clear? Now, just to complement the baseline that your colleague mentioned, there has been a lot of navigation papers that instead of just using at the history of an agent in terms of an unstructured set of frames, they build spatial maps. They consider how the camera moved, and they project those images into a 2D overhead map, and they'll take this overhead map as input for their policy. And instead of predicting immediate action parameters, as your colleague suggested, they can be predicting a location in the map. So they say, you need to go there. So they call this high-level policy. And then there is some very simple low-level controller, much like in our car environment, that takes you to that waypoint, to that predicted waypoint. Okay, so these are alternative versions. Well, it turns out that the one that uses a spatial map generalizes better to real environments. Why? Because those spatial maps will be represented as semantic maps. So you will not see the pixels, you will only see their semantic labels, much like in the driving paper where we see learning to drive via modularity and abstraction. The input to the policy will never be the pixels themselves, because once you put the pixels, because the pixels look very different from simulation, in the real world, everything breaks. So whatever you learn in simulation cannot generalize. So essentially, you take this hand-designed choice of, oh, I'll commit in this set of labels, and I'm going to build a policy on top of those labels. And because semantic segmentation works in the real world, my semantic, let's say, spatial map will be pretty good, and my policy will generalize. But this is not the point of this paper. The point of this paper says, why do we even need reinforcement learning for this problem? And why do we even need imitation learning in action space in that simulator? Okay, why we need to have humans play with their simulator and ask them to navigate to things and then take their trajectories, and these trajectories would be kinesthetic, right? We will have the state and the action of the agent and so on. So they question these assumptions. They say the problem is that RL is not sample efficient. We need insane amount of frames to learn to navigate. simply because, the RL algorithms are just not advanced enough. Simulators are super expensive to build, and they cannot be super diverse. So they say, how can I learn to navigate directly from passive videos? And they say, there are tons of videos on the web where people just wander around, okay? For example, some videos are for real estate. In real estate, there is a video that navigates you around the house. Now, again, there is an amazing computer vision technology, which what it does, it takes that video of the static scene and infers the camera trajectory. Do you see the beauty of that technology? So this is called SLAM, simultaneous localization mapping. So basically, you know for every time step how the camera has moved, which is precisely your action. So you don't need somebody to go in the simulator and start navigating there. You can just go in static videos in YouTube, take them down, and infer the camera pose. So this is precisely what they're doing. Okay, is that clear? Okay, and then once they have essentially those pseudo trajectories that they got in terms of visual features and camera poses, they can learn a policy. Now, they can learn a policy. And that policy can be, we can learn it now from imitation learning. We have a lot of demonstration data of actions. I mean, okay, the actions are not like turn left, turn right. They're just the camera pose moves from here to here. That's fine. And we can imitate using standard imitation learning techniques. Now, this is not what they decided to do. Now, this is the beautiful thing. Let me tell you, the reason they didn't decide to do that is because when you do exploration, there is an insane multimodality problem. For example, you may ask me to go out of the amphitheater. Most of the times, to be honest, I use this way of going out because I'm closer, but sometimes I can use this other way. Do you see? And if you just train policy with behavior cloning, and you make mistakes because of that. Does this make sense? So they do something very different, which is the following. And they get state-of-the-art performance, so that's why we need to pay attention, okay? They say, I will take passive videos from YouTube, and essentially what I'm going to do is I'm going to make a map, set of images. I don't even need to make a map, but I need to have the set of waypoints of where I walked. I can make that map, and each frame is going to be a location on the floor because I know the camera pose. Do you see? I know the camera pose. And for some of those nodes where I was, I can also have the associated visual frame that the agent saw when he was there. Okay, is that clear? Because each time you walk, not only you are a node on the floor on that spatial map, but you also see something. Okay, so these nodes come with some visual observations. Okay, all right. And what I'm going to do is I'm going to learn, given a new environment, I'm going to watch around the image, I'm going to compute a depth, and then I'm going to project it down to make a map. And then the only thing I'm going to do is I'm going to infer possible waypoints on the floor and evaluate which one of those waypoints are closer to the goal. So let's see exactly what this means. It means that you have a map so far. This is the representation of your history that your colleague said. So just to be clear, for navigation, many times the agents don't use, as we said, an unstructured set of frames, but they rather build a static scene and they infer their past histories as waypoints on that static scene. And by the way, the Roomba robot that cleans your house exactly does that thing. It doesn't have a sequence of frames. Okay, it just does mapping and keeps track. Okay, where did I clean? Did I clean here? Let me go and check there. Evaluates this is a cleanable area, no, and so on. That's it. And the new robot from Amazon, Astro, also does amazing SLAM. All right, the same thing. So it goes from a video all the way to that map. And that map is not just a map, what you see here with like projected the visuals essentially on the floor, but also has waypoints of where the agent has been. Okay, here is the goal image. It is actually taken from there, and you're somewhere in the map, and you want to figure out which way shall I move to go closer to the goal image. So what you do is you hypothesize some waypoints on the floor. By the way, this waypoint better not hypothesize within the wall because you cannot interpenetrate the wall. But this is easy to infer because you have a depth, local depth inference. And then you hypothesize waypoints, and then you evaluate them. Which one of those is closer to the goal image? Do you see? And then once you evaluate them, you say, great, this is my next waypoint. I'm going to go there. And now you update your map. and you're like, okay, this is another red. I decide to go here. Let me evaluate new possible waypoints, and so on and so forth. Now, let me show you. This process has 4 different modules. 2 of them will be learned, and 2 of them will be hand designed. Okay, so now we're going to see which ones are learned and which are hand designed. So again, what is the process? You go in your environment and you build a map. So we're not going to follow your baseline. Okay, it's just a different representation of the history. We'll make a map. We'll exactly map exactly where the agent has been as waypoints on the floor. We will be at each time step hallucinating possible future waypoints. For example, I'll hallucinate one here and one here and one in the back because this is the free space. And I will evaluate those waypoints. This is very important. This is the learned part. And once I do that, then I will just go there. And you know what? Going there is, again, not going to be learned. You're just going to do a very simple local policy that has to do with obstacle avoidance. Make sure you don't bump on obstacles and so on, and just takes you from one waypoint to the next, much like in the driving setup. Okay. So here is the topological map again. So this is very important. This is the representation of our history. Okay. This is the representation of our history. And here are the 4 modules. The global policy. So let's start. So we're here. And the first thing we need to do is we need to do step 3 to hallucinate new waypoints. And this is not learned. It has to do with obstacles. Like whenever you have space to go, you just go there. Now, ideally, there needs to be some learning there because you don't want to step, for example, maybe it's a water on the floor, or maybe it's, how your moms get upset if you step on dirt. So you can put some learning there, but it's a very easy learning problem. It just tells you, given the immediate vicinity, where can you step? So this is step 3. Now, step 1 comes in and gives you, this is the most important step, and gives you the evaluation of those new waypoints hallucinated in combination with the goal image. Then there's the selection of the waypoint based on which one is closest to the goal, based on your estimation from step 1. And then there is the local policy step 2 that takes you there. That's it. And the only thing that step 4 does is checks whether you're done. Did I achieve my goal or not? Okay. And if you decide that your goal is nearby, it tells you which direction you should move to go to that goal. So step 4 kicks in only when your goal is visible from where you are. Okay. How should we be selecting sub goals? So we said we want to minimize the agent's distance to the goal image. Okay. And here is the most important thing. Here's the most important thing. This is the global policy. And the global policy will be a graph neural network. And what will be the nodes? The nodes will be where you have been so far, and your feature will be the image that you saw when you were on that location. And these are some extra nodes. These are your hallucinated locations. For those locations, there is no picture because you've never been there before. You didn't see how the world would look if you go there. Now, it would be very easy to simulate because you just take the 3D map and then make a picture, but you don't need that. You're just going to put this waypoint as location with respect to you in your egocentric coordinate system. So you instantiate those nodes. You instantiate the goal is another node, by the way, the goal image. And then you train a graph neural network to predict distances for those waypoints. And you know how to predict distances because you have those trajectories that you got from YouTube using SLAM, where every trajectory had the goal image and intermediate waypoints. Okay. Is that clear? This is the most important thing to realize, that there is a graph that when I compute my distance, I take into account my history, that some nodes have a visual observation and some nodes are hallucinated, and that your goal is to compute the distance of the hallucinated waypoints to the goal. All right, so this is what you train for. Okay, this is the most important part of the paper. Because now, once you do that, and now you can evaluate all your waypoints, but yes, so the edges have to do with the delta pose, how far away and in which orientation change the nodes are. So these delta pose are also taken into account during graph convolutions. Okay, they enter into the edge features. Okay, and then given the goal and so on, you say, all right, you can compute for each node how far away it's from the goal. Now, each one of them is also, you can compute how many steps away is from where you are right now, and you add these two. So how much steps I need to go to the hallucinated waypoint, and how much is this hallucinated point away from the goal based on my estimation. And that's how you pick one waypoint, and you just go there with a local policy. And the local policy is super simple. It's just the shortest path computation based on your local depth map. Okay, that's it. It's not learned. The expansion of these hallucinated waypoints also is not learned. You just look at the depth, you project it down, and whenever you think that you can fit as a robot, you just put a waypoint there. That's it. Very, very simple. Okay. Valid explorable areas to the graph, but very beautiful representation, guys. Very general, very general. And this is very important to read in detail, because I'm not sure we're going to see other navigation papers, and because the representation of the history is super central. And here is the last step 4, and it's all about whether you're done or not. When should the agent stop exploring? Well, you see that this goal image is actually kind of visible from here. And when it believes it is within sight from the goal, it can predict the goal location, predict the direction that you need to move to go to that goal location. All right, that's all. So this is it. These are the 4 steps. The most important thing is the global policy that takes into account the goal and the map you have so far. Now, in the beginning, where you just dropped in that home, there's going to be only one node red in your map and a lot of hallucinated ones. Okay. Then you'll evaluate, you'll select sub-goal, you'll use local policy to go there, you update your graph, you check whether you have the goal is within sight, and then you repeat, okay, if it's not. Is that clear? Okay. Right, and we said that the step 1 and 4 are learned, and the middle 2 steps are deterministic and hand designed. We said that you can go either online, or you can go in simulation environments and not look at the actions and read off the actions using computer vision technology, SLAM specifically. That's what we said. And this is also what they did. And they build maps out of this type of tours of static houses. Here it is, how the tour looks like. And then they check, they make that, they make this trajectory as their history. Each time they add hallucinated nodes, and they compute distances for the ones that actually showed up in the trajectory, because for the others you actually don't have ground truth data clearly. Okay, so the experiments are very interesting because of course they stayed in the simulator to do apples to apples comparison with their reinforcement learning methods, and previous methods do much worse than this method. And why it says with noise and without noise? Because a big part of this method, guys, is estimating your pose, how the camera moves. So they say I can add noise into the camera pose estimation, or I can just remove the noise. All right, that's why. And the truth is that the camera noise has a big impact, as you see in the performance. I'm not sure in general how important this is. When you are an active agent, you can move slow enough to have a good estimation of your pose. But in general, you don't need the metric maps very far away. You just need a local metric map. As you see, these people maintain a topological map of the environment. Okay. But in any case, as you see, with much less GPU resources, without any interactions, these people are doing really great, which shows that it's very important to learn to use passive data in the right way for the right problem. Okay. All right, so to be honest, that's it. This is what I wanted to tell you. And then they went to this real estate data set that I told you with the videos that they show to advertise houses that are for sale. So instead of taking those videos from simulation environments, they took them from YouTube. And again, they learned to move in the real world. And the beautiful thing of taking those videos from YouTube is that you don't have now the sim to real gap. Do you see? So the pixels are exactly the same way that you'll see them in the real world. All right. Now, having said that, the numbers are still not that great, right? I mean, in general, it's not that we've solved the problem. So there is a big, margin for improvement. But I still think that was a very nice paper that challenged approaches for reinforcement learning for navigation. Okay. And this is the last slide for this topic. Do you have any questions? Any questions, guys? And before we move on to our next topic? No. Okay. So if we want to do reinforcement learning or imitation learning from images, it is always helpful if your encoder does not start from random weights. Okay. In the same way, I mean, there are two different things. You show up, you go in the new video game, and you don't need to learn to see and to play the video game at the same time. I mean, you can assume you can see the monsters, see the stairs, see the cave, see the tunnel. And then the only thing you do at your friend's house when you play is figure out how to win the game. You don't learn to perceive it. I mean, you become faster at figuring out the monster and seeing the sphere, but it's not that you learn vision from scratch. Okay. Now, our agents so far, I mean, the way we have presented them, they essentially learn to see from scratch, random weights, each time we, train them in a particular environment. Is that clear? Even in that navigation paper that we just showed, all right? If you start your visual encoder from random weights, it's as if you've never seen any pictures before in your life. And now you both want to learn to see and, decide distances between goal images and non-goal images, as well as you both learn to see and get some good features, as well as estimate the distances between goals and images, correct? Now, the question is, how can we learn to see before we learn to act? And the truth is that babies in the first years of their life, they move very little, but they move their head a lot and they can still see around a lot, okay? All right, now here is the thing. When we humans say learn to see, we understand learning to see objects, learning to see properties of objects, their poses and so on. Here, in today's lecture and whatever we've been doing so far in the computer vision field, by pre-training and the visual pre-training, we don't mean that. We don't mean to recognize objects or seats or chairs. The only thing we mean is to have some good feature representation in our weights of our network, so that if you put a small layer on top, you can fine-tune that network for a target task without needing a lot of training data. That's what this means. Okay? Is that clear? And by the way, if many people, if you ask them, what is the revolution that deep neural nets brought? They're going to tell you the most important thing for neural networks is that you can learn some weights, okay, that you can transfer actually across tasks. And before that, with SVMs and so on, we didn't do that. We would train a different machine learning model for each different task. Does this make sense? Well, now we can share. So this is huge already. So this is already huge, okay? So now we want to learn how we're going to learn those features, okay? So there is this topic of self-supervised learning, which started around 2000, let's say 15, okay, or 14. And the topic of self-supervised learning is as follows. It's a type of representation learning. You want to learn the representations from unlabeled data. So it's different than supervised learning, because supervised learning is about learning representations using supervised labels. Now, the truth is that supervision is not binary. There is a weak supervision, weaker, stronger, strongest, and so on. Okay, but some form of human annotations. So if you want to pay some people or not to pay, and the humans give you some annotations, then you're supervised. If you don't pay humans to give you annotations, then you're self-supervised, let's say, okay? Now, self-supervised specifically will tell you the following thing. You'll get data sets where humans haven't annotated anything, and you create toy tasks. You call them pre-task tasks, okay? And from this pre-task task, you have the supervision. So because you create those tasks, okay? Just to be concrete, you take an image and you rotate it 45 degrees. And then you ask your network, okay, given this rotated image, what is the rotation? And you train your network to spit out, oh, this is 45 degrees. And you know the labels, not because a human annotated the image, but because you created that rotated version of the image. Okay? Is that clear? And you hope that by training your network on your self-generated labels, that you will learn awesome representations that will be able to transfer across different tasks with very little annotations. That's the hope. Okay? Yes. So you want to be able to use them in downstream tasks with very little annotation, something like this. So you have your pre-training data and you train your model on your toy task. We'll see some super ridiculous tasks here. Okay. But despite the fact that these tasks are ridiculous, the weights of the model are still very useful when you transfer them, and you can either freeze them or fine tune them. But we'll see, okay, most of the times you should be able to freeze those, fine tune a very tiny layer on top for your downstream tasks. Okay, let me give you an example. Maybe the downstream task is object detection. Okay, and you want to be able to use very, very little object detection labels to do well on that task while having pre-trained your visual backbone on some toy tasks. Okay, is that clear? All right. So do you guys know the ImageNet dataset? Okay, ImageNet dataset was constructed for image classification. That was the first version of the dataset. It had 1 million images paired with their category labels. Okay, and it took 3 years to make because you had to filter because some annotations were noisy and so on and so forth. Now I want to tell you. So here is another depiction of what I told you. You make a toy task. This is the rotation. So here you take a bird, you rotate it 90 degrees. You need to ask your network to predict 90. And then you go to the supervised task, which is the image classification, and you will need very little data to adapt your feature extractor. So this is precisely what it shows in the previous picture. Now, up till 2019, if you wanted to do object detection, the best pre-trained features that you would get to transfer them to object detection would be from image classification pre-training. Is that clear? So what you would do is you take your feature encoder, which could be a CNN, you will train it to classify images of image into their image category labels, and then you would take those features and then fine-tune it for object detection, which is a very different task than classifying image, okay? And if you would pre-train with ImageNet versus, initializing those weights from scratch, you will get a huge boost. Is that clear, guys? Okay, great. Now here's what happened. So we were here at the Greek Cafe in 2015, and the discussion was as follows. When will be a self-supervised pre-training method beat supervised ImageNet pre-training for object detection? Do you understand the discussion? And why this is important? Why is it important for a self-supervised method to beat a supervised method as good learning, good pre-training representation? Yes?
It's so much cheaper data-wise.
Yeah, because then we can get rid of ImageNet and we don't need the new ImageNet to train good visual representations. Okay, great. Now, so then we said, okay, what if this is possible within 1 year? Okay, and by the way, back then, the papers would show, weights initialized from scratch, 30%. Weights initialized from ImageNet classification pre-training, 45%. Okay, so you would always compare with the random weights backbone. Like nobody now would ever think to compare with random weight backbone. In any case, so this bet was won by Jitendra, who said, no, there's not going to be done within a year. It's going to take longer. So actually, let me tell you, the bet eventually was figured out in 2019 from Ishan Misra, had a paper. I'll show it to you. It's called Pretext Invariant Self-Supervised Learning. So from 2014 till 19, 5 years, there are a gazillion self-supervised papers trying to beat the supervised pre-training. So then all the papers would show, supervision with ImageNet, and you get, let's say, 40%, supervised with our method, then you get 31, and then next year it's going to be 33, and then 35, and and the numbers were going higher and higher. So now I'm going to show you a bunch of those gazillion set of papers that were trying to get good representations, and eventually what worked, okay? So here a bunch of pretext tasks. These are all the toy tasks. Some are a little bit more kind of difficult and serious, like generative tasks. So you want to generate images, like autoencoders that we saw. This is self-prediction. And so in these last three, we may go in more details. Self-prediction means you have your signal, which can be an image or a video. You hide some part of the signal, and you train the model to get it back. That's what means self-prediction. All right. And this is a very famous slide from Jan LeCun, because, you know, there are these gazillion papers that say, oh, no, self-prediction is about predicting the future. No, self-prediction is about predicting some part of the image. No, self-prediction is about predicting the past of the video, and so on. He said, you can take your signal, mask anything you like, and generate it back. And this is still self-supervision. Okay. It doesn't matter when it's the future or condition in the past, or it's some part of the image. As long as you mask something and you generate it back, you know, it's a form of self-prediction, and it's a very legit, you know, self-supervised task to go for. Yeah, to predict the past from the present, the future from the past, the top from the bottom of the image, and so on and so forth. All right? And there are a lot of, now this, for example, autoregressive generation, this was an ICML Best Paper Award, Pixel CNN, where they make a model to autoregressively predict pixels in the image. Okay, so pixel RNN, I thought it was the Best Paper Award. Mask generation means that you take an image and you mask a part, and then you want to generate it back. And I'll show you, we'll come back to this. And BERT model, this is the very famous mask language pre-training, okay, that has worked super well. What are the two tasks that the language people do? Well, one task is you take the sentence and you mask some words, and from the surrounding, you try to implement those words. So this is called masked language pre-training. And the other is called language modeling, where they predict the future word by word. And they both do well. They both do well. There are different forms of masking, as LeCun said. You can mask the middle and predict it from the surrounding, or you can mask the future and predict from the past. And, you know, these people are very lucky because they have the softmax that can help them handle multimodality very easily. They have a vocabulary, and they predict using softmax for words. Okay, while in vision, you know, it's hard to discretize the image and so on. So you will always, when you mask something, there's always multimodality. A lot of things can be there, but we'll see how different methods do that and so on. Now, so this was about self-prediction. Now, there is another set that has to do with contrastive learning. And contrastive learning means, you know, you have some images and you create toy tasks that put some images close and some images far. And you train your network to map images to feature embeddings. So you can take distances, use those features, L2, using L2 norm of the difference of the vectors, and they need to reflect the supervised distances. That's it. So basically the standard contrastive loss that actually we have also used, if you remember. Actually, we used it when we trained the comparator network, when we talked exploration with memory, if you remember that paper. They say, okay, here is my pair that I want to put close. Make sure you minimize this norm, and make sure the pair that I want to put far is above a specific margin. Okay, so this means that if the Y's are different, if the labels are different, make sure that the features of those two images are put far away. And does anybody remember to tell us what was the toy task that we had come up with on that paper with the memory? It's called Exploration Through Reachability. This is the paper. Do you remember what was the toy task that we came up with to train our comparator network? Just to remind you that comparator network would take two frames, the same weights, was a Siamese network, so the weights are like Siam, like twins, and then we'll get two feature vectors, and then we would supervise those feature vectors. Do you remember how we created the positive and negative pairs to be able to train that network? Yes.
One frame was reachable within like k steps.
Yeah. So whatever was reachable within k steps was positive. They're my positive guys that you need to be close to me, and whatever is beyond k steps are negative. Correct? Yes. And k was a hyperparameter. Very simple task. Do you see how naive it is? And still it was used to train good features for our comparator network to work. Now, this was not the task of self-supervised because we actually use the comparator to compare. It's not like we take the comparator features and we fine-tune them for object detection, But I'm just saying that there also we use that toy task. All right, here's another very simple loss. So instead of contrastive loss that compares pairs and says, okay, put those close, put those far, triplet contrastive loss uses triplets and says, make sure you put the positive guy closer to me than the negative guy. That's all. Okay, that's all it does. And the general, let's say it's called info-NC also, this loss. The general contrastive prediction, when let's say you want to predict the future, but there are many other possible futures and you have multiple images as negatives, then way to predict is this loss. So essentially you have a plus, you are the current frame, which is X, you have an actual positive pair, which is the actual future frame, this is your X plus, the negatives are all other possible frames from your data set, okay? And you want to say, I want to make sure that X plus is much closer to me than any other guy, okay? So this is the loss that we usually use. And this is also the loss that exactly shows up in the contrastive predictive coding paper, which is going to show up in a few slides from now. Okay, so we don't just have triplets, we have the positive guy and tons of other negatives. This is variational autoencoders. That's another thing, and we've seen this. And you know what? You can take them the encoder. In fact, one of you had this suggestion the other day when we asked what pretext task shall we use, and you suggested we can do autoencoding. And here is GANs, which we also have seen. And again, the generator. I mean, I'm not sure how you will be able to. Okay, yes. So you may use the discriminator weights as pre-trained weights. I mean, this really hasn't worked really well. This is precisely the picture from this ICML paper, at least. They use a raster order to predict pixels one at a time. Okay, again, this is the pixel task of generating one pixel at a time. And these are some other, so this is 2016 paper, where it masks the center of the image, and it asks the network, it's a CNN, to condition on what's visible to in paint the middle, and it's called context encoders. Okay, so you learn features by in painting. All right. Now this back then really didn't work. Okay, meaning that all these were features, papers that were proposing, oh, I'll use this pretext task. I'm going to mask and I'm going to in paint. I'm going to add noise and I'm going to clean. Or I'm going to take an image, chop it into patches, and then I'm going to have a network take those patches and predict the relative arrangements. So you need to predict that this, for example, in the top left corner. All right. Oh, I'm going to do something else. I'm going to rotate an image, and then I'm going to predict the rotation. Okay. So all these are different papers that people tried as toy tasks so that they learn good visual features. Okay. In fact, this paper did well for quite some time. So this Dorsch 2015 actually did pretty well for 1-2 years. And this is exactly the contrastive prediction that I told you earlier, that you have the actual future, which should be closer to you than any other guy in the dataset. Okay, and here is now what actually worked. Okay, so, and actually there is a very good picture from this paper that said the following. Many previous works were trying to come up with a toy task, for example, rotation or some other transformation, like take two patches and predict their arrangements. And then they were training a network to predict that rotation, okay, or predict that arrangement. And he said, this is not the right toy task. We're going to propose something different. He said, instead of predicting and being equivariant to the transformation, what you should do instead is to be invariant to the transformation, which means what? Take an image, rotate it, featureize both of them, and ask the features to be close. Don't try to recover the rotation. Just ask the representation to be close. That's what they said. All right? So they say, instead, what we're going to do is we'll take an image, we'll take an augmented version of the image, featureize both of them, and tell them be similar. So that's why they call it pretext invariant. They want the representation should be invariant as opposed to be able to decode the transformation. Okay? And this was the first paper which was able to beat the supervised pre-training, as you see here, when you would use those representations for downstream task of object detection in the Pascal dataset, I think, in the Pascal VOC, yes. So this is an object detection dataset. Because back then, imagine, didn't have object detection, or all these COCO were not, out or not. Is that clear to you guys? So it took like 4 years for a pretext task to actually beat the supervised pre-training. Okay. Yes.
So this is just another pretext task, right?
Yeah, it's just another pretext task. Now, the interesting thing is that Jeff Hinton has a 1980s paper that does exactly that. He takes an image and augments it and put it close. So they do exactly that. Of course, much different architecture because they couldn't train it otherwise. But the task is not new, meaning it existed. It's just that potentially they did it better and so on and so forth. And they resurrected it. Is that clear now? Okay. Now, 1 year later, Hinton and his students wrote another paper exactly like the 1980s, but with an updated architecture. And it's called CLR, like Simple Contrastive Representation Learning. And yes, so this is doing also very well. It also beats the previous paper, but the idea is very similar. So it's only the details that differ. Let me tell you some details. You take the cat, you augment the cat, you shift it, you rotate it, you crop it, you change the color. And by the way, this is so crazy that, you would ablate, oh, I did all these 7 augmentations. If you do this and you don't do that, you get this number. If you do more of the augmentation, you do that number. So you just ablate your augmentations. And what they did is now you're at the top of the encoder, and they added an extra little layers there. They added some extra layers there. And then you would, compare similarity here. So you would put your loss right there as opposed to directly here. But then you will discard this guy. So this is going to be used only for pre-training, and you're going to use your base encoder as a downstream feature learner. All right. So you help a little bit the features by adding some extra layer, which can, discard rotation. Maybe for object detection, it's important to know the rotation of the cat. So that's why you will discard it only from the top layers that only used during self-supervision, and then you discard them when you're fine-tuning the encoder. So super low-level details, guys, here, but they're kind of important. So here is how it is. You have 2 images. You augment both of them. And here's a pair. Here's another pair. Now, you want to put those close, and you want to put them far from the elephant. All right? Whatever's in your batch. So every image will consider all other images in your batch as negatives. Okay? Now, the representation, they say you'll discard this guy. You'll only use the encoder. Is that clear? So that's, by the way, some new thing here. This is one important addition. All right. Yeah. So this is how you do learning. You take your batch, you have the ground truth similarity, you take inner products essentially, and make sure that these inner products are higher than the cat and the elephant inner product. All right. And essentially you have a type of softmax loss where you say, oh, I want to make sure this is higher than the comparison of all other pairs in my batch. Is that clear? This is exactly the info NC loss that we said that generalizes the contrastive to X plus, and tons of negatives. So this is the X and X plus, and these are tons of negatives. So this is exactly how it works. Yeah, this is exactly how it works. Very simple. And then you can go and fine tune this representation for a classification task, a detection task, and so on and so forth. Here are all the crazy augmentations that they do. You can also mask or Gaussian noise or change the color, all crazy things you do, okay? And, look, they're able to go much, much higher. This is Pearl. This is the previous paper that we just discussed. And this is supervised. And, yes. Oh, and this is image classification. This is not detection, all right? This is image classification. And they're able to do better by doing this pre-training for the classification task. Is that clear? All right. So now another task that we have seen is time contrastive. Pre-training is exactly what your colleague said earlier. The fact that there is a video and you take 2 frames that are nearby and you say put them close, and you take frames that are far away and you say put them far, and that's how you self-supervise your representation. Again, using contrastive, but over time, as opposed to an image and augmentations. All right. Now, what can you do with them? Now, here is where you do all this self-supervised thing and so on. So how do you use it? Well, you use it in this way. You use it for your policy. Now, this is the encoder of your policy where reinforcement learning is going to sit on. So you're going to jointly train for the self-supervised training, this contrastive training that we said with augmentations. Here is the augmentations you're going to consider, all crazy things, and the standard reinforcement learning. And in this way, your image encoder, because now you're going to train a policy not from the joints of the robot as input, but rather the image itself, is actually will require way, way less samples than if you you initialize the encoder with random weights. And this is not very surprising. Okay. Now, the important thing is that you train the policy, because the policy is going to find new images that you haven't seen before. Those images, you should bring them back and use them for self-supervision, augment them, and so on. So you don't just do, okay, I'm going to first pre-train, and then I'm going to fine-tune. Do you see? Because what data are you going to use to pre-train? As your policy improves, the data that it collects are better. So you should use this better data for self-supervision as well. Is that clear? Okay. Okay, so what are the results? Well, the results are, of course, much, much, much better than all previous methods, simply because of the pre-training. I mean, and this is a soft actor critic using the state, by the way, which means no pixels, no pixels. Of course, this is doing super well. This is doing slightly better than that. Actually, no. Well, it is unfair comparison, but it is there for the sake of, okay, how well you would do if you have a golden state representation that is very low dimensional. Now, here is the catch. When you have this golden state representation, there is no pre-training you can do. You need to start your weight from scratch, your encoder, okay? Because it's very targeted for this particular robot. I mean, potentially you can also do some, augmentations and pre-training of that MLP. I don't think they don't consider that here. I think they start this from scratch. Well, this guy is pre-trained using visual augmentations that we saw, correct? This is a paper that, although the idea is like obvious, is famous paper. It's called Curl, Contrastive Unsupervised Representations for Reinforcement Learning, okay? So there is no reinforcement learning contribution here. You just copy-paste the best self-supervised method from self-supervision for reinforcement learning. That's all that happens here. And guess what? As the field of self-supervised learning progresses, there are new models that actually can work better. Now the SimCLR is not state-of-the-art anymore, or at least it is state-of-the-art if you are not willing to fine-tune the encoder. If you fine-tune the encoder, this is the winning task. What is this task? We've seen this before. It's actually masked prediction. Let me tell you, it's extremely simple. You have an image. This is the image of that bird. You mask a big part of the image, like 80%. You encode only the visible patches using a transformer, all right? So now you compute features for each of those patches just by self-attention layers of transformer. Then you instantiate features from the patches that you didn't see, and you add them here. And again, you have a decoder, which again is a lot of self-attention layers. And you supervise by predicting the pixels of the image. That's it. It's called masked autoencoders. It is an autoencoder in the sense that you want to generate the same image, but there is a masking. So it's not image input, image output. It's masked image as input, unmasked image as output. Okay? All right. Now, this is doing better now. This is doing better. Now, when you use this, of course, as a downstream task, you're not going to mask. You use the whole visible pixels and you pass them here to the encoder. The beautiful thing with transformers is that they can accept any number of patches as input. So you can train them here with 15% of patches of the image, but you can test them with 100% of patches present. Do you see? This is the beauty of the attention inductive bias, correct? Okay. And here are the results, which are totally, the visual results don't say a lot. I mean, even if the images that are generated are blurry, still the encoder weights are pretty great as a downstream task. And indeed, here is another very recent paper that came out where it goes in a huge data set of egocentric actions. It's called Ego4D, 3,000 hours of egocentric data collected across many, many universities with many, many researchers being part of this and a lot of users. They wear the camera here and they do different things, climbing, cooking, knitting, everything, typing on the computer. And they do some masked autoencoding on every frame of this data. And then they use the pre-trained encoder for downstream task and simulation. And they say, look, I do better than random weights or random weights with contrastive pre-training and so on, which is fine. So basically they show indeed masked auto-encoding. It is the state of the art in visual cell supervision. It is also useful for downstream robotic tasks. Is that clear? Okay. Now the last thing that I want to discuss today is the following. I think it is amazing how, ImageNet to be created requires insane amount of money for Amazon Mechanical Turkers to go and annotate, and insane amount of engineering effort for filtering and quality checking of those annotations that the Amazon Mechanical Turkers supplied. And are people, is there anybody that doesn't know what's an Amazon Mechanical Turk? Okay. Now it turns out recently the best visual representations for many tasks, not for robotic downstream tasks, just to be clear, whatever we're going to discuss is not the state of the art for robotic tasks, but for many other tasks, comes from data that humans annotated, but not with payment. So they captioned images and they put them on Instagram or they put them on Facebook, and nobody paid them to do this captioning. It was just there. All right. So then you download those images. And you download a lot of images, not 1 million, but like 300 million. And then you're going to do this contrastive training that we're going to discuss. And the resulting encoder is going to be pretty golden. I'll show you some amazing generalization properties of that representation that beats all those previous tasks that we saw, this self-supervised. Okay. Yes. But it doesn't do better for downstream action tasks, just to be clear. Okay, which is natural because before, if you remember, we pre-trained using actions of humans and objects moving around, and now we'll pre-train about pictures that you guys post on the web. There's not much activity. Nobody's going to put pictures of him climbing or doing tedious daily tasks in the kitchen. You all the time put very fancy, kind of exquisite and interesting things that actually are not very useful for the robot doing the kind of boring and things that we tested on, okay? So the training of this model is particularly simple. What you have as input is pairs of images and captions, okay? So what you're going to do is you're going to encode the image into one-dimensional vector. So you have here a bunch of images. So these are vectors for each one of them that you have in your batch. And then you're going to go to every caption with a language encoder, okay? Which again is a transformer here. Here they use resonance because when they did that, transformers were not very yet. This is a bit earlier paper, like 2 years now, I think, to 2020. Okay, but this is a transformer here, I think, text encoder. So you'll get 1D vector for language, you'll get 1D vector for image, and the only thing you're going to do is you're going to compute inner products, and you're going to do this contrastive training that I told you, but it's going to be, which says essentially that this inner product should be higher than any other here, okay? And any other here in the table. And this inner product should be higher than any other here and here. Is that clear? So you want this image and this language to match better than this image paired with any other language, or that language paired with any other image. Do you see how simple contrastive training? Very simple, but very large scale, very large scale. And the thing is that, how do you classify an image? Well, you classify an image because once you train, let's say, that network, the way you classify new images is that you consider a long list of object categories. You make dummy sentences of the form of a photo of a dog, a photo of a car, which you encode each one of them. You see that image with which one it has higher inner product, and then that's how you classify. All right. And let's compare those 300 million weekly annotated captioned images versus the 1 million images of ImageNet that Amazon Mechanical Turkers label with category labels. And it turns out that as you go to different data sets here, you see this one, this is ImageNet, this ImageNet version 2, this is another one, this is ObjectNet, this is Sketch, this is adversarial. In both cases, whatever was trained with the clip representation without any fine tuning, okay, is much, much higher than the model that was trained to classify images on the ImageNet dataset. Do you see? So basically, you take the image encoder trained from CLIP, okay, that was the CLIP model, and you test it on a gazillion different tasks, on gazillion different inputs, and it's doing much, much better than anything that we had before. Is that clear? Any self-supervised thing and supervised thing. I mean, here it beats the supervised, but if you self-supervise, also you're going to do better. Now, for robotic tasks specifically, if you do contrastive or masked autoencoding on images of activities of people, you do better, all right? But for these are all labeling tasks and recognition of objects. So here, naturally, the CLIP is going to do better. So here is a paper that used CLIP as the encoder of the policy. But unfortunately, they didn't compare with another form of self-supervision. I guess that if they did a different self-supervised task, it actually will do better. But of course, CLIP is doing much better than ImageNet pre-training. I mean, it is expected. Okay, so what they do is they take the image, this is their policy, and they pass it through CLIP, and they get to 1D, and they also have some history here with some LSTM and 1D, and they try to, act in the world and act in the home. And this looks like a super, super naive policy architecture in comparison to what we saw in the beginning of the lecture, where, the home was kind of modeled as a map, and the camera pose was taken into account, and so on and so forth. So, I mean, nothing great is going to come out of here. I'm just going to show that, this CLIP can be used as an encoder for downstream tasks and so on. Yeah, and again, CLIP is doing much, much better than ImageNet pre-training. And unfortunately, there is no comparison with another self-supervised training here, but that's all. And so basically, the takeaway of today's lecture is that if you want to learn to act in the world from pixels, learning to act and learning to see are two different things. Learning to see, you can use many, many other data sets and tasks to do that. The better you learn to see, the better you will do acting. Now, learning to see is not just pre-training your weights to have awesome visual representations. The priors you guys bring when you go to play Atari games is not about, oh yeah, I have pretty awesome weights on my neural net. You actually recognize situations. You recognize situations of what we saw, the key, the monster, the rope you need to jump, and the trophy you need to grab, okay? Now, this type of situation pre-training, how can we pre-train our representation to actually require situations and go much, much better than just, oh yeah, let me do better warm start on my weights as opposed to random weights. This is an open research problem. And we do expect that we're going to see a lot of progress in that direction, potentially in the next 3-4 years or something. So you're free 3 minutes earlier today. So have a great weekend, and I'll see you on Monday.